Hey everyone, welcome back! I made a lot of videos with solutions for mobile system design problems, but today I want to give you my toolkit with the 5 most important concepts to use in an interview. We'll break down each topic in detail, covering both the pros and cons, along with examples to help you build a solid foundation in mobile architecture. Alright, let's jump right into the first concept – API communication protocols. Communication protocols are the backbone of any mobile's app communication with its backend. They define how data is exchanged between your app and the server, influencing both reliability and performance. Today we're looking at 4 major protocols. REST, Representational State Transfer, is an architectural style for designing web services. It relies on stateless, client-server communication model and uses standard HTTP methods – GET, POST, PUT, DELETE. RESTful APIs offer a simple, scalable way for mobile apps to communicate with backend services, making them the most popular choice for mobile API design. Pros: simplicity. Easy to implement and understand, making it accessible to developers of all levels. Text-based communication. Messages are text-based, which means they are human-readable, making debugging and inspection straightforward. Easy to cache. Leverages HTTP caching mechanisms, specifically cache control headers, and works well with CDNs, which can improve performance significantly. Statelessness. Each request carries all necessary data, allowing servers to scale horizontally. Now cons. Overfetching. Since the server dictates the response structure, clients might receive too much or too little data. Metadata overhead. Repeatedly transmitting headers and other metadata adds unnecessary overhead. Validation challenges. It can be difficult to validate data integrity and format on the client without custom validation logic or external schema definitions. For example, OpenAI or Swagger. By the way, I highly recommend checking out Swagger, I personally used it many times. Lacks real-time support. REST isn't inherently built for real-time communication, so additional mechanisms are needed for dynamic updates. Next, WebSockets. WebSockets enable real-time, bidirectional communication over a persistent TCP connection, reducing latency for mobile apps. Pros: low latency, ideal for apps requiring instant data updates like live chats or games. Efficient data transfer, eliminates the need for repeatedly opening new connections, reducing overhead. Supports multiple data formats, handles both text and binary data. Cons: complex setup, more challenging to implement and maintain compared to the simpler REST model. Infrastructure demands, requires specialized infrastructure to manage and sustain long-lived connections. Network restrictions may be blocked by firewalls or proxies that restrict non-HTTP traffic. Next up, GraphQL. GraphQL is a query language that allows clients to specify exactly which data they need, offering a more flexible approach to API consumption. It was initially developed in Meta and later open-sourced. Many popular public APIs have adopted GraphQL, including Facebook, GitHub, Yelp, and Shopify. Pros: precise data retrieval, prevents overfetching by enabling clients to request only the data they require. Rich developer tooling, offers introspection and powerful tools like GraphQL for testing and debugging queries. Supports subscriptions, can handle real-time updates via subscriptions typically implemented over WebSockets. Cons: client-server coupling. The client becomes more tightly coupled to the backend schema, complicating API evolution. Implementation complexity. Setting up a GraphQL server and managing resolvers is generally more involved than traditional REST. Caching challenges. Standard HTTP caching mechanisms aren't as effective, requiring custom caching solutions. gRPC. gRPC framework built on HTTP2 and using protocol buffers is designed for high-performance communication with a focus on efficiency. Pros: high performance, delivers low-latency communication with small message sizes, which is ideal for resource-constrained mobile environments. Strong typing, enforces type safety through generated code, reducing runtime errors. Streaming capabilities supports various streaming models, including bidirectional streaming for real-time use cases. Cons: steep learning curve, more complex to set up compared to REST, requiring familiarity with protocol buffers and HTTP2 nuances. Specialized infrastructure may require additional server resources and configuration that aren't as widespread as REST. Non-human readable formats. Binary messages are difficult to debug and inspect without specialized tools. Alright, let's move on to the second concept, real-time updates. Real-time updates are critical for delivering a responsive user experience for applications like social media, messaging, or live streaming. Let's explore the primary methods. HTTP polling, the simplest method where the client sends periodic requests to check for new data. Pros: ease of implementation, relies on basic HTTP, making it universally applicable and simple to implement. Low initial setup, no need for persistent connections or special protocols. Effortless horizontal scaling. HTTP's stateless design simplifies distributing traffic across multiple servers. Cons: inefficient resource use. Regular requests can drain battery and consume unnecessary bandwidth even when no updates are available. Latency issues. Updates might be delayed if the polling interval is too long. Overhead from TLS handshake and HTTP headers. Repeated connections introduce significant overhead, especially for small updates. Heavy server loads. Repeated polling can put a strain on server resources when many clients are involved. Next up, HTTP long polling. Instead of frequent requests, the client sends a request that the server holds open until new data is ready. Pros: reduced latency, minimizes idle waiting times, leading to faster delivery of updates compared to simple polling. Better resource utilization, fewer overall requests when data is not continuously changing. Cons: connection overhead. After each response, the client must re-establish a connection, which can still introduce overhead. Server loads, requires the server to maintain many open connections, which can be resource intensive. Prone to timeouts and disruptions, requires strong error handling and reconnection mechanisms. Server Send Events, SSE. SSE establishes a one-way channel that continuously streams data from the server to the client. Pros: efficient streaming, provides a continuous flow of updates with minimal connection overhead. Easier than WebSockets, simpler to implement and manage than bidirectional communication protocols. Uses standard HTTP, built on the standard HTTP protocol, ensuring seamless integration with existing infrastructure. More efficient than long polling, reduces overhead by maintaining connections instead of repeatedly establishing and closing them. Easy debugging, the text-based format makes it straightforward to monitor and debug. Cons: unidirectional communication, clients can't send data back over the same connection, limiting interactivity. Keeps a persistent connection, requires server resources to maintain the connection. Now WebSockets. Hello again. As noted earlier, WebSockets support full duplex communication, making them an excellent choice for interactive real-time applications. Pros: true bidirectionality, supports simultaneous sending and receiving of data, ideal for collaborative apps and live interactions. Lower latency, maintains an open connection, minimizing the delay inherent in repeated handshakes. Cons: higher complexity and resource intensive. Push notifications, Apple Push Notifications service for iOS and Firebase Cloud Messaging for Android. These services allow servers to push alerts or data updates even when the app isn't actively running. Pros: background updates, can wake up or alert the app, ensuring that users receive timely notifications. Integrated with OS, leverages native capabilities, optimizing battery usage and delivery reliability. Energy efficient when used properly. The operating system handles the connection and message delivery, minimizing battery consumption. Cons: Not reliable. The most important is that they are not completely reliable. Message delivery depends on network conditions, device status, and platform restrictions. Third-party reliance. Dependent on services like Apple's APNS or Google's FCM, which can introduce external limitations. Payload constraints. Typically limited in data size and subject to delivery delays under certain network conditions. Users can opt out. Users can turn off push notifications in the app settings or at the OS level. Remember that. The third concept, storage. Choosing the right storage solution is vital for ensuring performance, security, and efficient data retrieval on mobile devices. Let's break down the key options. Key value storage. It could be user defaults on iOS or shared preferences on Android, ideal for small, unstructured data, such as user settings or preferences. Pros: speed and simplicity, fast read-write operations with minimal complexity. User-friendly built-in API provides straightforward methods for storing and retrieving data. Lightweight, low overhead makes it perfect for storing primitives. Cons: limited complexity, not suitable for handling large or relational datasets. Not secure. By default, data is stored in plain text. Sensitive information requires additional encryption layers like encrypted shared preferences on Android or keychain on iOS. Not suitable for large data. Performance drops noticeably with extensive datasets. Lacks schema and querying. Limited query support and no data integrity enforcement. Next storage option is database. Structured storage solutions like SQLite, Room, Realm, or Core Data on iOS manage complex data and relationships. Pros: robust querying, supports complex queries, transactions, and ensures ACID compliance for data integrity. Structured data management, ideal for relational data with defined schemas and indices. Object relational mapping streamlines data handling by integrating object-oriented principles. Cons: setup overhead, requires initial setup, proper indexing, and maintenance to avoid performance bottlenecks. Resource usage may consume more device resources, especially on older hardware. Higher learning curve, requires understanding of SQL or ORM principles. Next, file storage. Storing data as files, used for large, unstructured data such as images, videos, or documents. Pros: flexibility, easily handles big files without requiring a strict schema. Direct access, files can be managed and retrieved through standard file in-out operations. Cons: lack of querying, no built-in ability to query. Developers must manually manage file directories and permissions. Potential inefficiency. Without proper organization, file storage can lead to slow data retrieval. And finally, no schema or migration support. Managing schema changes can be challenging. Secure storage. Critical for protecting sensitive data, secure storage solutions like Keychain on iOS or Keystore on Android are essential. Pros: enhanced security, provides hardware-backed or OS-level encryption, keeping critical data safe from unauthorized access. Integration with biometrics, works with system-level authentication, Touch ID, Face ID, Android biometrics to further secure data. Cons: limited to specific use cases, best suited for storing small, sensitive data like encryption keys and user credentials. Storage limits, often restricted in size, and may require careful management of what data is stored securely. Complex APIs. Implementation is more involved and requires thorough testing to ensure data remains secure. And again, no schema or migration support. Managing schema changes can be challenging. The fourth concept, pagination. Pagination is a technique used to divide large sets of data into smaller, manageable chunks, typically called pages. Instead of loading all data at once, an app fetches and displays a limited number of items at a time, For example, 20 posts per page. This improves performance, reduces memory usage, and minimizes network load, ensuring a smooth user experience. It prevents long loading times and app crashes by fetching data incrementally. Pagination also enhances scalability, making it easier to handle large datasets like social media feeds or product listings. Let's look at 4 common pagination strategies. First, limit offset pagination. Data is retrieved in fixed-size chunks using 2 pointers: limit, the number of items per page, and offset, the starting point in the dataset. For example, get posts limit 20 and offset 30 fetches 20 posts starting from the 30th item. Pros: easy to implement, simple to handle in code since you just request a specific number of items and specify the starting point. Stateless on the backend. The server doesn't need to keep track of previous requests or session data. Efficient for small to medium datasets. Works well when you don't need to load huge amounts of data, as each request fetches just the required chunk. Simple to understand, intuitive for both developers and API consumers. Cons: performance issues. With large offsets, the database may scan through many rows, slowing down response times. Inconsistent results. If new data gets added or removed, the positions of items shift, which can make some results go missing or appear twice. Inefficient for real-time data. Not ideal for frequently updated datasets, as offsets can quickly become outdated. Second, page-based pagination. Page-based pagination loads data in chunks using a page number and a page size. Instead of calculating offsets, you just request a specific page. For example, get posts page 3, page size 20 to get the third page with 20 items. Pros: easy to use, simple for both developers and users since you just pick a page. Clear navigation makes it easier to jump to a specific page, at least in static datasets. Cons are very similar to offset pagination. Inconsistent results. If data changes, items can shift, causing duplicates or missing entries. Slower for deep pages, large datasets still require scanning many rows. And not great for real-time data. Items move between pages as data updates. Next up, key set pagination is a method for retrieving a set of records from a database by using a unique identifier, like an ID or a timestamp, to track where you left off. Instead of counting rows or skipping over large numbers, it fetches the next set based on the value of the last record. This way, you avoid performance issues that can arise when using traditional pagination, especially with large datasets. Pros: faster. It is much faster for large datasets because it doesn't need to scan through all previous records. Stable results. It ensures the results are consistent, even if the underlying data is changing while you're paginating. Efficient. Works well when data is sorted by a unique field like a timestamp or an ID. Cons: limited sorting. You must sort the data by a field that can act as a key, like an ID or a timestamp. It doesn't work well with complex sorting. Leaky abstraction. Pagination is tied to the database, exposing details about data storage, for example, the ordering field, which could break things if the schema changes. No random access. You can't jump to arbitrary pages like page 5, you must go through the data sequentially. And last one, cursor-based pagination. It is similar to keyset pagination in that they both rely on a position-based reference rather than a simple offset, ensuring efficient performance on large datasets. But cursor-based pagination is a more flexible method where a cursor is used to track the current position in the dataset. The cursor is often a unique identifier, but it can also encode more complex data, such as the state of sorting. The client sends this cursor back to the server to retrieve the next set of results. It is commonly used in API-driven systems like GraphQL. Additionally, cursor-based pagination can incorporate multiple sorting or filtering parameters into its cursor, unlike traditional keyset pagination, which typically uses a single field. Pros: efficient. Just like keyset pagination, it is efficient with large dynamic datasets and handles data changes well. More flexible. The cursor can include more information, making it versatile for more complex queries and sorting scenarios. Scalable is great for APIs where clients need to paginate through large datasets without impacting performance. Separates pagination from SQL. The API does not reveal any information about the underlying data storage or sorting. And cons. More complex backend. Cursor-based pagination can be more complex to implement than key-set pagination, especially when dealing with cursor encoding or decoding. State management. It may require additional effort to manage the cursor state, especially when combined with multiple filters or sorts. Less transparent. Can be harder to debug issues because the cursor is an opaque token. And finally, the last concept, dependency injection. Dependency injection, or DI, is a core design pattern that enables you to supply a class with its dependencies rather than letting it create them internally. This means the class doesn't have to worry about instantiating its own dependencies. It just gets what it needs, which makes your code more modular and easier to test. Okay, why use dependency injection? Loose coupling. Your components don't create their own dependencies, so they are not tightly bound together. This makes it easier to swap out implementations or update code without breaking everything. Testability. By injecting dependencies, you can easily swap in mocks or stubs during testing. This means you can write cleaner unit tests without relying on actual implementations. Maintenance and flexibility. It improves the overall structure and maintainability of your code. When dependencies are injected, you can manage and configure them centrally, making it easier to update the application as it grows. For iOS, you can simply inject dependencies via initializers or properties. If you need a more scalable solution, try using Swinject to manage your dependencies in a central container. On Android, manual injection through constructors or setters works fine. But for larger projects, Dagger is a powerful option that generates code at compile time for efficient dependency management. Alright, thanks for watching. If you enjoyed my content, like and subscribe. See you in the next one.